Good morning. Thanks for joining me for this webinar. Before we start, I would like to thank Dan, Michaela, and the Gleeble team for having me today. The topic today here is physical testing, numerical models, and real processes. I'm Fernando Okigami. I work at the Hexagon Manufacturing Intelligence, specifically in the virtual manufacturing costing. So when we have a project at hand, we need to do three types of analysis here. We start from a system cost analysis, we do a modeling approach, and then we look at experimental simulations, for example. From a system cost analysis, we need to know what technology is available, what kind of process we want to tackle, and how reliable our results are going to be. The modeling approach is going to analyze what's happening at the process level or at the material level, depending on what we want to do and what the results we want to achieve. Most of the time, when we run a simulation, we want to also include some experimental results, for example, on what kind of input data we're going to use for the simulation, because that's going to be our correlation back in the real world. So we have thermal properties, mechanical properties. Sometimes we want to include also metallurgical properties. The agenda for today is the following, and we're going to cover quite a lot of topics. We're going to very quickly go through the fundamentals here, which is basically a heat treatment process and forging processes that are simple enough to simulate and understand from a physical testing perspective also. Then some basic understanding of how we're going to model certain processes, certain aspects of the material behavior. And then we're going to use that to test some of our hypotheses, for example, related to press hardening, which is a type of stamping simulation. And going forward, we want to check, for example, how we can use the same set of data to analyze resistant spot welding problem called liquid metal embrittlement. This chart is well known to probably everyone joining us today. It's how the material behaves. So you have information about temperature, phase transformation, mechanical response, chemical composition is going to affect all that, and it's a two-way communication. Now, if we think about process modeling, we can look at just one aspect of the process, for example, a specific location of a rolling process where we're going to apply a certain thermal cycle, and then we're going to apply a strain to the material to understand what kind of mechanical behavior we get out of that. And this curve is an example of heating up the sample, having a dwell time, and then you have some quenching happening, you reheat it, and then you cool it back to room temperature. Then you apply, for example, a certain strain, or you apply it until it breaks. And what you see here to the right is the simulation of this process. At the top right, what you see here is the heating process. Then you have the resulting microstructure of the heating. You can see volume fraction of austenite, how much austenite was formed there. And then in the end, we do a pull test to see how much it affected the mechanical properties. And you can see here it's breaking, where we have most of the material still in the ferrite condition, not really bainite or pearlite, which is expected. This is the animation of the same process, showing how it looks like, what it looks like once you simulate the exact same condition. Here we are visualizing temperature. I'll just fast forward it a bit. And then once it's back at room temperature, we do a tensile test. And then we see where the sample might break once we do the physical test. You can also do a compression test like this one. It's kind of the same curve. You can see here there's a heating, a dwell time, a quench, and then you keep it a certain temperature for a certain time. Here's the same thing. And I'll just fast forward here again, and then you do a compression test. You can see here that the faces in touch with the anvils are not allowed to move. So this is let's say a very high friction condition where you don't slide the surfaces. And this kind of bulge effect is what you get once you run the same experiment. And so you can run these experiments to extract valuable information. You can see here the one of the stress strain curves representing the material behavior. In this case, it's a compression or tensile, and then you release, you have some residual plastic strain. And to run the simulation that you just saw, we need more information, of course, besides the flow curves. We need Young's modulus, Poisson ratio, density, and so on, because this is how the material behaves, and this is how it's modeled in the finite element perspective. So we need this kind of information. And most of them, if not all of them, you will need some form of experimental data to input to the simulation. So you can't run just the simulation, the numerical simulation, expecting it to fully predict what's happening in reality if you don't have experimental data feeding that, being fed to the numerical model. From a modeling perspective, it's really simple. Finite element, it's a very well-known way of modeling things. You can see here, for example, two examples where you have two beams and then you pull them, you model them like this. There are some very standard equations, the matrix form and boundary conditions and so on. This is not needed for today, but you need to understand, for example, how the data that you are feeding to the model is going to be used or how it's going to be calculated. So when you look at the results, they make sense. And just like what I mentioned, we need many different thermomechanical properties to run that kind of simulation. In this example here, we have a Young's modulus that's a function of temperature and phase fraction. This is needed, the phase fraction is needed if you want to include, for example, transformation to austenite and back into whatever other phases you want to form, martensite, bainite, pearlite, and also the thermal expansion coefficient. These curves were calculated analytically, and you can check if they are completely true or not based on experimental. You can validate if they are okay to use in the simulation based on experimental data that you run on a Gleeble machine. If you have data just at room temperature, that's fine. You can still run simulations like these ones, which is related to self-piercing rivets. These are very important aspects of the process, the joining process, because you want to know how much force that joint is going to resist before it starts to break. When you are joining the similar materials, this is how you do it most of the time. What happens if we have the material changing temperature during the process, like for example in a welding simulation or additive manufacturing, then we need data at multiple temperatures. And most of the time we want it to be from room temperature all the way to close to melting point, at least above solidus temperature, so we capture correctly what's the thermomechanical behavior. In that case, we're going to need thermal conductivity, for example, specific heat capacity, latent heat, and if the process involves very high energy, we need vaporization temperature to capture correctly and predict correctly what's the temperature resulting there. This is a simple welding simulation. Again, the numerical background here, the equation that you see to the left, these are just to illustrate or just to explain where the data from experiments are going to be used in case of the numerical simulation of the process. Looking at the right, you see the animation of the welding process. It starts from room temperature, and then you add material, the filler material. It melts, and then it solidifies and causes some distortion residual stresses to happen in the structure. And this is going to lead to the behavior that you're expecting, for example, when looking at distortion of the part. You want to predict the distortion. And another couple of examples of thermal conductivity and specific heat capacity in this case. You can see again that they are a function of both temperature and phase fraction. You can isolate a specific phase, for example, and just say, oh, other cases you might want to look, for example, at phase transformation from a very detailed perspective. For example, in this press hardening process simulation where the sheet is heated up all the way to austenitization temperature and then brought back to room temperature during a quench stage in the dies. And you want to monitor, for example, how much martensite you are forming or what's the cooling rate that you are expecting for certain locations of the die. And simulation can certainly help you with that. Simulation would need a lot of input data, for example, how the material transformation happens, and you can get that kind of information from the autometry test that you run on your Gleeble machine. You're going to need some flow curves, for example, because you want to model the heating phase and the cooling phase. You're going to need to extract that kind of information from the material that you're using to do the PHS. Now, if we think about the extreme case where you want to simulate the experiment that you're running, so you have a one-to-one match, this is an example of running a Gleeble test inside a numerical environment where you see the thermomechanical, electrical, and metallurgical process happening. This is very interesting because you could design your sample shape, how you're going to have the cutouts here. you can drive the thermal in a certain way and have the metallurgical transformation happen in the specific locations that you want. You don't need to guess how the current is going to flow. You can calculate that, for example, looking at the current density, and understand how the electric part is flowing, how it's going to generate temperature in that case by Joule heating, and how much stress you're causing in the sample by heating it up that much. You can change, for example, the shape of your grippers here, the anvils, in a way that it's going to change how the electrical portion of it is going to affect the thermal generation. But then you ask, why do we want to do all that? Why do we need, or why do we want to collect all that data and simulate the process? Because manufacturing processes are not simple things to simulate, and we need good, reliable source of data for that. We know that analytical calculations exist, but they only go so far in terms of providing you with accurate data. Every material behaves in a certain way. There's certain variations in the manufacturing process of the steel itself, so we won't be able to simulate everything. In this case, what you're looking at here is a PHS process that's very unique. You use Joule heating to heat up the blank. You don't use the furnace. And then you transfer it to the press. You can see here the temperature changing already between when you finish the heating process and then you transfer back to the press. Then you do the die quenching. In this case, we're looking at the differential cooling. Part of the sheet is being cooled by just free cooling air, and the other half of the sheet is being cooled by die quenching. And then we have some residual stresses, and then what phases we formed in there. And this is a very difficult experiment to perform because you have multiple cooling rates happening at different locations. You can see here in this picture the differential cooling, even in the die that's a rigid die touching the sheet. The temperature is not going to vary the same way as the rest of the sheet here. And there's another problem that also happens sometimes in PHS. It's more common nowadays to resistance spot welding process, which is the liquid metal embrittlement. This is a problem that happens when you have zinc coating and a substrate that's very sensitive to grain boundary penetration by the zinc. To the right, what you're seeing here is a Gleeble test of a certain material where the sample at the top is uncoated. The sample in the middle is coated, but we pulled it at a high temperature above austenitization. And the one down here, the third one, is the one that it's still coated, but we pulled it at the lower temperature, so below melting point of zinc. And you can see the problem is very apparent here. It's very clear where it happened and how it happened. Once you have that kind of information, you can, for example, include in your PHS simulation where you are expecting problems to happen. So the first animation here is just the forming, and playing at the same time where the liquid metal embrittlement might happen based on temperature and stress. So you can see towards the end, when the die is closing, you can see probability of LME happening in certain locations. And while it's doing the die quenching, this is where most of the problems start happening, because now you have the sheet trying to shrink, generating a considerable amount of tensile stress. All right, so now that we have information about the LME happening for a PHS process, why can't we not extend that to the concept of resistance spot welding that suffer from the same problem? In this case, we're looking at the door beam component that was PHS produced, and then it's going to get spot welded. The LME doesn't happen after the PHS process happening in this case here, but it does happen, for example, in Gen 3 steels that are being very intensively studied currently. So how can we do that? If we do tensile test the same way as shown before in a Gleeble machine, you can see here that the left-hand side is when you have no coating, and right-hand side is when you have coated. For the coated condition, you can see here that the crack starts and breaks the sample, and the sample doesn't knack. So there's a certain condition here that needs to be observed. In this case, we can use this information about not knacking in the coated condition to drive, for example, a condition of when the LME is going to happen in the spot weld. There's also research around using the extensive Gleeble data available for a certain class of material in this case here it's a high manganese alloy, to train machine learning models that can predict or try to predict when the LME condition is going to happen. So the tensile test data is going to give us a 1,000 feet view of the problem. It's not going to tell us exactly what's happening at the microstructure level. It's going to tell us the big picture, what it looks like once you try to pull the sample. So we use that information to build this database of bare versus coated material, the same substrate, but with and without zinc coating, to understand, for example, how much stress it can resist at a certain temperature before it breaks. And the curve fitting that you see here to the right is exactly that, how much peak stress at a certain strain rate was achieved before the material lost its strength. And that's over a certain range of temperature, which is when zinc is present in the liquid phase. Now, if we try to model the same condition, it's not very difficult because we know how it should behave and how to set up a finite element model. In this case, I'm showing here at the bottom left temperature, and to the right, I'm looking at the max principal stress, which is an indication of how much stress and in what direction the stress is present. And in this case, I'm comparing, for example, what happens when you have a coated condition versus an uncoated or bare condition, and how much force I'm getting out of the tensile test. Then if you think about it, can I map those results into a process simulation like a spot weld simulation? Yes, we can, because the concept of maximum principal stress, it's the same. So we want to look at the stress, in what direction, and then try to infer or how the crack is going to nucleate in this case. So this is a resistance spot welding simulation showing the max principal stress. First one, left bottom here, is a cutting plane through the center of the weld, just like this picture here at the top. And then to the right, what we're looking at is kind of an isometric view and how the stress is concentrated. You can see it tends to form rings around the weld, which is the red areas that we see here in the contour plot. And then I would say the final step would be, once we have the model and we can compare it with some experimental data, why not expand it and try to predict what would happen in a certain condition when you are in production, for example, manufacturing a car or using that material in a certain welding process. In this case, we're relying on experimental data published by University of Waterloo in combination with Auto Steel Partnership. And they ran multiple experiments with electrode misalignment. You can see this is the case number 1 here. It goes from 0 or no misalignment all the way to 10 degrees. We reproduced numerically what was experimentally done. In this case, the electrode misalignment from 0 to 10 degrees. You can see here a very interesting correlation. 0 degrees, the two pulses are as standard as not. The two pulses or standard weld schedule, as named by the paper, is showing higher LME than the optimizer 5-post one. We capture the same behavior here in the simulation. Also for the 2 degrees, the 5 poles, it's producing more LME than expected for the standard weld schedule, and we predicted that also in the model. The other condition was the gap between the sheets from 0 to 1.4 millimeter, which is the thickness of the sheets being welded here. And then we ran the same model again. You can see we got pretty interesting correlation. But what's interesting is you can use this kind of prediction to drive better how you're going to design your weld schedule, because now you can predict how LME is going to happen in what phase of the welding process. The two pictures that I'm showing here is the difference between applying a 2-post weld versus a 5-post weld. There are some differences in how much current is applied and duration of poles and cooling time between them. And what you're looking at here, the dashed line, is the weld schedule. The red line in the end is the retraction of the electrode when there's no forced cooling anymore. For the 2 pulses, you can see there is some LME happening in the first pulse and also when the electrode is retracted, while for the 6 pulses, most of the LME is happening between the first and second pulse. There is some happening after you retract the electrode. This is another interesting aspect. Can you improve the LME condition by increasing hold time? If you're interested in walking a similar path here, combining physical test data with simulation, going from simulating the sample test that you did all the way to process simulation like spot welding or press hardening, these are the main steps. So you're going to need to know beforehand what problem you're going to tackle, so your hypothesis. You do some thought experiment, run the simulation in your head, essentially think about what you're expecting, how you would perform a certain test. Not just the numerical simulation, but also the physical test. You don't have infinite samples, infinite amount of time to run all the possible conditions. And then you test some physical aspects of your hypothesis, of course, using a well-maintained, calibrated machine. Otherwise, you can't trust the data. Collect as much data as you can from the experiment. Don't collect just what you think you need. Collect everything that's available, temperature, force, strain. If you have digital image correlation, make use of that. You won't be able to use raw data directly in the simulation, so you need to do some data curation. It's not hard at all. You need to filter the data, for example, use an origin or create a curve fitting, and then use that curve as input for your simulation. That's an important step because you need to trust the input data that you have for the numerical model. Then you model the experiment in the computer. Don't jump all the way to the process simulation. Think about how you're going to validate the data that you acquired from your Gleeble test. So simulate that condition and make sure that the data that you collected is in line with what your numerical model is predicting. Of course, you need to know what you're doing, and that's what I call modeling. Simulation is just running the model and looking at the results. That's not what we want. We want to model the problem. And then look at the results and criticize them. Think about comparison between your experiment and your numerical results, and they should match if you follow all these bullets. And of course, share your findings and help advance your field, because you running the simulation, running the models, and don't sharing the information, the knowledge with others, there's little value in that. And if you have any questions, we're going to have the QA session. Let me know. Here's my email. Shoot me a message if you're interested in knowing more how to run the numerical simulation of Gleeble test, or how can you compare data, how to build a material card. Thank you.